If you want to understand literally anything, from the smallest atom to the biggest galaxy, you first need a way to measure it. We needed a common language, not of words, but of numbers. This is the story of how we built that language, the invisible framework that makes all of modern science possible. But for most of human history, it was a total mess. Imagine trying to build something, but every single person on the team has a ruler with different markings. That's what it was like. A pound in one village wasn't the same as a pound in the next. It was chaos. And this wasn't just annoying for trade, it put a hard stop on sharing knowledge, which is, the entire foundation of science. I mean, really think about that. How could you possibly build on someone else's discovery, or even just repeat their experiment to see if it was true, if the very tools they used to measure the world were a mystery to you? It was a huge problem, and it absolutely had to be solved. So let's start there. We're going to step into what I like to call the measurement maze. This first part is all about that history of confusion and why finding our way out was so critical for us to move forward. Because without a shared system, pretty much any kind of collaboration was a nightmare. Every single calculation, every blueprint, every scientific finding had to be painstakingly translated from one system to another. Progress was just incredibly slow, and it was full of mistakes. This lack of a shared language was really holding humanity back. But then, out of all that chaos, this beautifully simple idea started to emerge. What if we could just create one single, universal language of measurement for everyone? And that brings us to our next section, the rise of the SI units. And here it is. Meet the hero of our story, Le Système International d'Unité, or, what everybody calls the SI system. This was the answer, a single, logical framework that would become the absolute bedrock of modern science. And at the heart of it all are these core base units. Look how simple this is. All those confusing pounds, stones, and yards, gone. In their place, we get the meter for length, the kilogram for mass, and the second for time. It's just so clean, simple, and best of all, universal. All right, so let's zoom in on these fundamental three. And this is the amazing part, with just mass, length, and time, you can describe almost everything in the entire physical world. First up, we have mass. Now, it's really important to remember this is not the same thing as weight. Weight is about gravity pulling on you. Mass is about how much stuff, how many atoms you're actually made of. And for that, the SI unit is the kilogram. Now this is where things get really clever. This slide shows a huge leap in thinking. See, the original meter was literally the distance between two scratches on a metal bar kept in a vault in Paris. But what if the bar gets scratched, or expands a tiny bit when it's warm? So scientists redefined it using something that never, ever changes, the speed of light. Now a meter is the same everywhere in the universe, for all time. And they did the exact same thing for time. A second used to be based on the Earth's spin, but it turns out our planet wobbles a tiny bit. Its rotation isn't perfectly regular. The new definition? It's based on the incredibly stable vibrations of a cesium atom. This lets us build atomic clocks that are so precise, they won't lose a single second in millions of years. It's just mind-boggling. Okay, so we've got our unshakable base units, but now we get to see where the true genius of the SI system really shines. It's not just about the units themselves, but how you can scale them from the impossibly small to the incredibly huge. And the way we do that is with these simple prefixes. You just add kilo to meter, and you've got a kilometer, perfect for measuring roads. Or you add nano, and you have a nanometer, perfect for measuring a strand of DNA. It's such an elegant way to talk about the very, very big and the very, very small. Take this number, for example, 1/billionth of a second. Instead of writing out all those zeros every single time, we can just say 1 nanosecond. It's a fundamental unit of time in things like computing and high-speed physics. And that right there is the true power of this whole system. You take one base unit, the second, and with just a handful of prefixes, you can describe both the crazy fast operations inside a computer chip and the slow, grand dance of the cosmos. Which brings us to our final section, and really the most important point of all, the power of agreement. Why is just having a shared language of units so completely transformative? Well, the power comes from treating units not just as labels, but as tools for doing math. The little symbols, like M for meters or S for seconds, we can treat them just like we treat X and Y in an algebra equation. You can multiply them, divide them, and combine them to create totally new types of measurements. Here's the perfect, simple example. If you measure a distance in meters and you measure the time it took to travel that distance in seconds, you just divide one by the other. And the units follow the math. You get meters per second, the unit for speed. This simple act of combining units lets us figure out and understand all sorts of complex ideas. And really, that's what it's all about. A scientist in Japan can pick up a research paper from a physicist in Brazil and know with absolute certainty that their measurements mean the exact same thing. This shared language is what powers global collaboration on everything, from building the International Space Station to hunting for new particles at CERN. It really makes you wonder, doesn't it? The simple act of agreeing on a ruler completely transformed our ability to understand reality itself. So, if we could achieve that same level of crystal clear collaboration in other really complex areas, well, what other universes are just sitting there waiting for us to unlock?